Well, hello, my little triglets. How are you all today? Today we're going to jump right in to the section 5.8, and it is called Applications of Trig Functions. We're going to abbreviate it Trig Fun, because we all know Trig is very fun. All right, let's just go right into the story problems here. It says, you have a friend that's 100 feet away from you on the ground taking videos of your terrified expression as you go up in a hot air balloon. After the video, you wonder how fast you actually were going up to make you so terrified. So let's draw a quick sketch of that. So on the ground, you have a friend standing here going to take a video of you 100 feet away from where the balloon went up. The balloon went up. Here's our hot air balloon. And it's got a happy face on there. And all we know is that after a little bit, the angle of elevation to the flight of the air balloon is 37.7 degrees. Oops. 37.7 degrees. That's after, just a couple seconds. So that's the first angle of elevation. The second angle of elevation, 1 minute later, so 1 minute later, the angle of elevation is 76.2 degrees. So angle of L. All right, so let's draw that. So from the ground to here, the first angle of elevation was 37.7. Then the second one, going up to the hot air balloon, this whole angle here, I'm going to write it out to the side, was 76.2 degrees. So what we want to do is figure out how fast you were going up. So first of all, we got to figure out how far we've traveled. Now I know it was 1 minute, so we can figure that out in a little bit. We're going to figure it out how fast you were rising, and we want to put it in miles per hour. Okay, let's look at our picture here. I have two different triangles. The first thing I'm going to do is I'm going to find A. The second thing I'm going to do is I'm going to find B, because what I really want is C, because we started timing right here. From here to here, for C was the 1 minute time frame, so that's the part we need. So looking at the smaller triangle, we'll look at this red triangle, whoops, right here. And we have A is opposite of 37, and 100 is adjacent, so that's tangent. 37.7 equals A over 100. So figure that all out. I got A to be about 61.8 feet. Okay, so then the next part, we'll do a blue triangle, this large one. So across from the 76 angle, we have B and we have 100. So it's still tangent of 76.2 equals B over 100. And I got B to be 407.1 feet. It's a weird looking B. Okay, so now we have to subtract those two to get C. So B minus A is C, and I got C to be 345.3 feet. Okay, and that's traveling feet per minute because we timed it for 1 minute. So now we have to do the conversion. So we're going to take 345.3 feet per minute, and we're going to change that to miles per hour. So first thing I'm going to get rid of is the minutes. So I know 60 minutes is 1 hour. Then I'm going to get rid of feet. 5,280 feet is the same as 1 mile. So let's see how fast you are going to get that terrified look on your face. Multiply straight across, divide by 5,280, cancel minutes, minutes, feet, feet. We have miles per hour. left, and I worked it all out, and I got 3.9 miles per hour. Woo, you were cruising. No wonder you were scared. Okay, let's go to our next example. Next, we're going to talk about bearings. Bearings or headings. This is used in navigation. Now, navigation can be in the sky, it can be in water, it can be surveying, lots of different places, okay? So the main thing that's different than the way we draw our angles is you're either going to come from the north or from the south. And then you're going to tell if you're going east or west. So, for example, here's our grid, and I have an angle coming there. I'm coming from the north, that's the closest one, and I'm heading to the right, which is east. Let's say this is 43 degrees, so your heading would be north 43 east. That's how you would do it. So from the north towards the east, and it's 43 degrees. Okay, so if I put one down here, and I said, this is 30, but I want to know this one. I want to know angle B. Okay, so from the south, because that's the closest between north and south, I am going 60 degrees towards the west. So I say south, 60 west. From the south, 60 degrees to the west. All right, let's try an example of this. So let's say my brothers who are sailing in the Caribbean, which they did last spring, they navigated their own path. They got a big sailboat. There's five. I have five brothers. So they wanted to navigate by themselves. So they left the port. Let's say we have some land here, and there's a harbor right here. We'll say H for harbor. And the water is out this way. Here's the water. And they left the harbor. They went for 25 miles on a bearing of 442. Let me say north 42 east. So estimating from the harbor, here's your north, here's your east and west. So about 42 from the north headed east would be approximately there. Okay, so they started heading out to sea, and they went for 25 miles. Okay, then they turned 90 degrees clockwise, and they went 18 miles south 48 east. So what we need to do is make a 90-degree angle here, and I'm going to put in another north and east and west line. So if this right here is 90, how much would this one be? Now that's our 48 right here is actually this, because I'm coming from the south. Whoops, I put it in the wrong place. Let me back up here. It's right here. From the south, 48, going to the east. So that angle's 48. Now they're going for 18 miles, so let's continue this. And then it says, how far are they from the harbor and what is their bearing of the boat to the harbor or from the harbor? So basically what we want to find out is how far that is and what is, I'll do it in green, what is their bearing from the harbor? So this angle right here. Okay, so really Pythagorean theorem is how we're going to find x. So 25 squared plus 18 squared, that equals 949. You take the square root of that and you get about 30.8 miles. So this is 30.8. So if they ever got in trouble, they have to be able to tell the people back at the harbor, where they are, how to find them. Now, what about their bearing? Well, we know that this small blue angle is 42, but what is this large green angle? Well, we know this is 90. So how are we going to find that? I'm going to redraw this triangle. Here's our right angle. I know this is 42, this is 18, this is 25. I need to find that angle. Because it's a right triangle, I have opposite over adjacent. So tangent, I'll call it theta, of theta is 18 over 25. Do inverse tangent of 18/25, and I got 77.8. Now we just have to put the letters with it. So where are we coming from? The north. We're going 77.8 to the east. So that's what you would label it. All right, so the drawings get kind of complicated, but everyone can do them. All right, last idea here, last type of problem. We're going to do simple harmonic motion. This is kind of a physics idea. Simple harmonic motion is like a pendulum swinging back and forth, back and forth. So we have a basic formula that we've been using. So we're just using the A and B. We usually do C and D also. So A is usually our amplitude. In simple harmonic motion, they call it the displacement. How far off is this equation displaced? How's it changed? B is still the period for one wavelength. Okay, in other words, how long is one cycle? And we still use 2 pi over b to figure that out. Now another thing we're going to talk about is F, which stands for frequency. And frequency is basically the number of cycles per unit of time. So if we're talking minute or whatever. So it's kind of the inverse of what the period is, because that's how long it is for one cycle. This is how many cycles fit into 1 unit of time. So we can say that F is 1 over P over the period, or B over 2 pi. Because if this is 2 pi over B, then this is the reciprocal of it. Okay, now let's do one simple question with this. I want to figure out the equation, or draw the graph. If I have a spring attached to the ceiling and I stretch it and let it go. Let it go. All right, I want to know the equation. Well, I'm giving you the equation, -10 cosine pi over 6t. I want to be able to draw that graph. So let's think about this. Here's a piece of ceiling tile. We got a spring. I'm going to stretch it down and then let it go. So it's going to go up and down, up and down, up and down. So if I just look at this first section, the up and the down, that looks like an upside down cosine graph. So if we think of this resting as our x-axis, we should be able to come up with an equation. So here's our x and y grid. If I have here and here, so the -10 means I'm going to start down here at -10. The pi over 6 is the period. This is one wavelength. Actually, back up. I'm getting ahead of myself. This is B, and 2 pi over B is one wavelength. Well, our one wavelength stops right here. So we got to figure out how long that is. Well, 2 pi over 6, make that 2 pi times 6 over pi. Pi's cancel, I'm left with 12. So this spot right here is 12, one full length. And if we're talking seconds, it's 12 seconds. So that's how you can draw it from the description of the equation. You can draw the graph. Or I should be able to give you this graph and you should work your way back to that equation. All right, well, I'll see you in class and we will have fun doing some more of these applications. Ta-ta for now. Trig love is still out there. Don't forget.